Hello students, welcome to the online lecture series of Basics of Computer Network. Myself, Assistant Professor Mr. V.R. Vadekar from Department of Electronics and Telecommunication from Matoshi College of Engineering and Research Center, Nasik. Let's start with our today's discussion. As we know that we are studying unit number 2, that is error detection, correction and data link control. So let's start. Remember, in last lecture we have studied about a linear block codes. That what is linear block code? Why we call it as a linear? Because the XORing of any two valid codes, it generates another valid code. After that, we have seen the subset of linear block code, that is a single parity check. We came to know about the encoder and decoder function of single parity check. What happens if there is a single bit error? If there are more than one bit error, how we are going to, if we are going to increase the redundancy, then how receiver it is going to able to detect as well as correct the error. So let's start with our today's topic. Today we are going to study cyclic codes. So let's start with cyclic codes. Now, cyclic codes are special linear block codes with one extra property. In a cyclic code, if a code word, it is a cyclically shifted or rotated, the result is another code word. So let's suppose we are going to take this 7-bit data A0, A1, A2, A3, A4, A5 and A6. So we have the data 0, 0, 0, 1, 1, 0, 1. So now according to this property, what we have to do it, we have to move the value of A6 to A0. It means we are going to rotate it. And correspondingly, the see on this figure that value of A6, that is 1, it is shifted to the position of A0. The new word it is created and it is denoted by B0. So you can say B0 is equal to A6. Similarly, the value of A0, it is shifted over here, that is B1. A1 shifted to B2. A2 shifted to B3. A3 shifted to B4. A4 shifted to B5 and A5 shifted to B6. So from this, can we say that B0 is equal to A6, A0 equal to B1, A1 equal to B2 and so on up to A5 is equal to B6. So in this rightmost equation, the last bit of the first word, it is wrapped around and becomes the first bit of the second word. See the A6, value of A6, it is shifted to this first bit of this second word. You can see that. And then each bit it is shifted to its corresponding next bit, next position. Now in this we are going to discuss about a cyclic redundancy check, polynomials and cyclic code analysis. Now this table, it is going to show you a CRC code. So you can observe it from the table. The data word, it is of 4-bit and code word it is of 7 bit. So you can observe it for each data word there is a corresponding code word it is there. Now in order to understand this one, now we are going to see the example of data word 1001, that how this code word it is being generated. So please observe this table guys. Now we are going to see how this code word it is being generated by means of encoder and decoder. So you can see it, this is a CRC encoder and decoder. In the encoder, you can observe it, the data word that is A0 to A3, it has a k bits. Over here, k is equal to 4 as you can see it. And the code word, it is denoted by n, which is n bits. And over here, n is equal to, you can see that 3 extra bits R0 to R2, it has been added to data word. So it become 7 bits. Now, you can see that the size of this data word, it is augmented. Augmented means it has been increased its value by adding n minus k zeros to the right hand side of the word, right? So you can observe it, this is your original data word, and this extra 30, how we are going to calculate it? Remember, it is n minus k. So over here it is what? 7 minus 4, which is nothing but your 3. So we are going to append 3 extra zeros to the right hand side of this word. So the generator, it has, see it over here, it has a 7 bits input, whereas the output it is of 3 bit. Now this n bit result, it is a fed to this generator, and then generator it uses a divisor. You can see it uses a divisor of the size n minus k plus 1. So it means 3 plus 1 it is what? 4, because n minus k it is a 3 plus 1 it is 4. And remember guys, this divisor it is always a predefined and it is agreed upon by some rule. And this divisor it has been used by the encoder as well as by this decoder. Now the quotient, and before this one I want to tell you, this generator it is going to divide this augmented data word by the modulo 2 division. As we know, as you can know the arithmetic division, but over here we are going to use what? Modulo 2 division. And the whatever the quotient it is there, we are going to discard it, and the remainder, that is R0, R1 and R2, it is appended to this data word to create this code word. And you can observe it, this is your decoder. This code word it has been sent to the receiver. The decoder it is going to receive this code word, and possibly it is corrupted. So a copy of all n bits, it is fed to the checker. You can observe it, instead of a generator we have a checker at the decoder side. So it is of n bits, and over here it is what? 7 bits. So the remainder which is produced by this checker, it is called as syndrome, as we have seen in previous lecture. But in previous lecture we have seen the syndrome it is of n 1 bit, but over here the syndrome it is of 3 bits, that is n minus k bits, which is fed to this decision logic. Now this decision logic analyzer, it has a simple function. If the syndrome bits all are 0, if these 3 bits all are 0, then the four leftmost bit of the code words, it means this one, B0 to B3, they are accepted as what? Data word, original data word, that is A0 to A3, and it interprets as no error. But if the syndrome value it is non-zero, then these four bits are discarded as error is introduced during transmission. So now we would understand this by taking one example. So suppose, as I already told, we have a data word 1001. So along with me, you also note it down in your notebook so that you can understand it. Now the encoder, it takes a data word, and we are going to augment this data word by means of a three zeros, as I already told, that is n minus k, three zeros. So this is the dividend, it becomes 100, 100. It then divides this augmented data word by this divisor, and remember this divisor, it is predefined, it is fixed as shown in figure. Now the process of this modulo 2 binary division, it is same, it is that of your arithmetic division. However, for addition and subtraction, we are going to use, XOR operation, which performs both. Now, in each step, a copy of divisor, it is XORed with the 4 bits of the dividend. You can see it. We are going to make over here the XOR operation, since this is a modulo 2 division. So instead of subtraction addition, what we are going to do it, we are going to do XOR operation. Now see that how we are going to do it. Always remember, if the leftmost bit of this dividend is 0, the step, we are going to append this divisor as it is over here, because we are going to multiply this divisor by 1. So you can see it. So it would become 1011. So now you have to perform the XOR operation. As you know, XOR operation, since 1 1, it means 2 bits are same, so output is what? 0. Now 0 1, 2 bits are different, so XOR of it is 1. Similarly, the XOR of these similar bits, it is 0, as this is discarded now, its value is 0. Now we are going to pull down this 0 over here, so it would become a 4 bit. Now what I told, that is, if we are going to see the part of this dividend, this is now dividend, and its leftmost bit is 0, then we are going to use a 0 as a divisor. So you can put it over here, 1011 multiplied by 0, it is all 0. You could observe it, the XOR of these two similar bits, it is 0. The XOR of these two similar bits, again it is 0, and the XOR of these two dissimilar bits, it is 1, and this is discarded because its value is 0, so we are going to discard it. Now we are going to pull down the value next 0 over here. Again you have to check it, the leftmost bit, it is 1, then we are going to use a 1011 as a divisor, so this is multiplied by 1. So again, XOR of 0 1, it is 1, XOR of 0 1, it is 1, XOR of 0 0, it is 0, and this is also 0, and it is discarded. The last 0, it is now pulled down, So it becomes 0 double 1 0. You are going to observe the leftmost bit, it since it is a 0. So we are going to multiply this divisor by this 0. So it would be all 0. Now XOR of these two bits is 0 because same bits. XOR of two dissimilar bits, it is 1. Similarly, two dissimilar bits, 1 0, it is a 1, and this is discarded. So nothing here to pull down. So we are going to stop this division. So this is the remainder, that is the 110, and we are also going to discard this quotient. We don't use this one. So what is remain now? It is your remainder. What is the remainder? 110. So what we are going to do it, this is nothing but your R0, this R1 and this R2. Now we are going to append this remainder to this data word. So it would be 10011110. So this is the code word that is generated that you have observed in the table. So in this manner, we are going to find the code word for all remaining data words. So hope so you understood this division. Now, talking about a decoder. Now we are going to consider the two cases, guys. The first is the receive code word. It is no error, it is there. Since the code word that we have transmitted, it is 10011110 as just we have seen in the example. So no error in this one. So we are going to first see the no error, error transmission. The decoder, it is going to does the same division process as this encoder, and this remainder of this division we are going to use it as a syndrome. Remember, if the value of the syndrome, if all 0 it comes, then data word it is accepted, otherwise it is discarded. So let's see. This is my code word, and the dividend, it is a predefined, that is 1011. So again, what I told, we have to see the leftmost bit, it is 1, then we are going to use a divider as a 1011. So this is multiplied by this 1, so we are getting 1011 over here. Now we have to find the XOR of these two patterns. Then the XOR of these two similar bits, it is 0. XOR of these two dissimilar bits, it is 1. XOR of these two similar bits, it is 0. This is also 0, but so it is discarded. Now we are going to pull down this 1 over here, so it would become 4-bit word. Now we are going to observe the leftmost bit, that is it is a 0. So 1011, it is multiplied by with 0. So it is 0. Now we are going to take all zeros as a divisor. Now you have to find the XOR of 10, it is 1. XOR of this 20, it is 0. XOR of 10, it is 1. And this is also 0, but we are going to discard this one. So next one we are going to pull down to this. So again we are going to check the leftmost bit is 1. So we are going to use a 1011 multiplied by 1. So 1011 as your divisor. Again, now we are going to do the XOR operation over here. So you can see it 11. So output is 0. Similarly, XOR of two similar bits is 0. XOR of these two similar bits, it is a 0. And this is discarded. Last 0 it is remain, so we are going to pull down this 0. So again you need to check the leftmost bit since it is a 0. So we are going to multiply 1011 by 0, so it would be all 0. Then you can find the XOR of this and you would get, this is discarded, 3 bits syndrome, that is R0, R1 and R2. Since all the values of syndrome it is a 0, then we are going to take this 4 leftmost bits as a data word, and we are going to accept this data word as 1011. So hope so you understand this. division. Now guys, we are going to see the division which has an error. What is that error? See, this is this error. While transmitting this code word, earlier it was a 1, but due to the corruption it become what? 0. So now we are going to take 1000110 as a code word, and as you know 1011 divisor, it is predefined. So observe this leftmost bit 1. So 1011 is multiplied by 1. You would take 1011 as your divisor. Again, guys, the same procedure step by step we are going to follow it. Now we are going to do the XORing of these two dissimilar bits. It is 1. XORing of these two dissimilar bits, again it is a 1. XORing of these two similar bits, it is a 0. And this is also your 0, which is discarded. Now we are going to pull down this 1 over here, so it was become 0111. Since the leftmost bit it is a 0, now we are going to multiply 1011 by 0, so it is all 0. So the XORing of these two dissimilar bits, it is 1. XORing of these two dissimilar bits, again it is a 1. And XORing of these two dissimilar bits, it is 1. So 0, 0, it is also 0, which is being discarded. Similar bits are there. Now this 1, it is remained. We are going to pull down this value. So now we are going to observe the leftmost bit, that is a 1. So 1011, it is multiplied by 1. So it is, we are using it as a divisor. Again, we are going to do the same operation, that is XOR operation. Two similar bits. So output is 0. XOR of two similar bits, again it is a 0. XOR of this two dissimilar bits, it is a 1. And this is XOR of same bits, it is a 0. This last 0, it is remained. So we are going to pull down this 0 over here. So again we are going to check the leftmost bit, it is a 1. So we are going to take it, sorry, over here it is 1 should be there, sorry. So 1011, it is multiplied by 1, so we are getting 1011. Last XORing operation we are going to do it. So the XORing of your 0, 1, it is 1. XORing of 0, 1, it is 1. And XORing of same bits, that is 0, 0, it is a 0. So nothing here to pull down. So we are going to stop this division. So what is remained? It is a syndrome, that is R0, R1 and R2. So it is a non-zero. So it means somewhere the data, it is corrupted. So we are going to what? Discard this data word. So hope so you got the concept of, CRC encoder and decoder. Now let's start with a new topic that is called a polynomial. Now, a better way to understand cyclic codes and how they can be analyzed, is to represent them as polynomial. Now, a pattern of zeros, 1, can be represented as a polynomial with coefficients of 0 and 1. So the power of each term, see, this is, first you would understand this is the data, this is a bit pattern given as a name A0 to A6, 7-bit pattern. Now the power of each term, as we know, this is power x raised to 0, x raised to 1, x raised to 2, x raised to 3 and so on. So the power of each term, it is going to show you the position of each bit and the coefficient. See, this is 1, 1, these are nothing but the coefficients. So coefficients shows the value of the bit. So in this figure, that is, you can see it in figure number A, that how we are going to represent a binary pattern in its polynomial form. So you can do it, this 1 into x0, again 1 into x raised to 1. Now its value is 0, so coefficient is 0, 0 into x raised to 2, 0 into x raised to 3, 0 into x raised to 4, 0 into x raised to 5, and last is 1, so 1 into x raised to 6. So you can observe it, the value of this, it is a 0. And we know the anything raised to 0, it is 1. So 1 into 1, it is what? 1. and x raised to 1, so 1 into x, it is your x. All mid terms, in between terms are zeros because coefficients, their value is 0. So what is remaining? It is x raised to 6. So in this manner, guys, you can see that how we can represent the binary pattern into its polynomial form. And even in this in this figure, you can observe it that how we are going to removing all the terms with zero coefficients, and we can represent it in its short form, that is a 7-bit pattern. We can represent it in it just by using three terms. So hope so you understood this one. And similarly, guys, if instead of a 7 bits, if your data bit it is of 24 bits, right? And remember, if as like this one, three ones are there, A0, A1 and A23, and rest all the 21 zeros are there. So you can just represent the polynomial by using this three terms, that is x raised to 23 plus x plus 1. Now, just we would have a quick, review of the polynomial that you already know it, but so now degree of polynomial, guys. So if suppose you have equation x raised to 6 plus x raised to square 2 plus 1. So if you would been asked what is the degree of the polynomial, it is nothing but the highest power in the polynomial. And remember that degree of polynomial is always less than the number of bits in the pattern. So it is 6 over here. If you want to do it, this addition of polynomial that you already know, but suppose you want to do it modulo 2 addition, and suppose that you have this two equation, x raised to 5 plus x raised to 4 plus x raised to 2 and x raised to 6 plus x raised to 4 plus x raised to 2, and you want to perform the modulo 2 addition. The modulo 2 addition, it would give you just x raised to 6 plus x raised to 5. These two terms get cancelled because what we are going to do it XOR operation. So XOR of x2 and x square and x square, that is the two similar bits, so it is 0. Similarly, XOR of x4 x raised to 4, it means again similar bits, it is 0. But you would find it x raised to 5 XOR with no x raised to 5 term, it is there. So two dissimilar bits are there. So we are going to, it would give you the answer x raised to 5 and x raised to 6. Similarly, if you want to multiply this x raised to 5 into x raised to 4 plus x raised to 1, now we are going to add this power, so it would become x raised to 10. Simple. And if you want to divide x raised to 7 divided by x raised to 4, that we already know, then we are going to do the subtraction of the power, that is x cube. Now, one more thing before seeing the divisions using polynomial, you should know the shifting of bits. Suppose 10011, it is a binary pattern, and you need to shift this pattern to the left by 3 bits. So as we know, what would be the resultant? It would be 10011 triple 0, it is there. So we are going to shifting to the left. So if you want to find the equation, this is the equation. This is 1 plus x, rest are 0. So directly x raised to 4, it is there. And similarly, so this equation, polynomial equation, would become what? X raised to 7 plus x raised to 4 plus x raised to 3. Because you have to multiply these terms by the x raised to power. That is x raised to 0, x raised to 1, x raised to 2, x raised to 3. So x raised to 3 value is 1, x raised to 4 value is 1, x raised to 5, x raised to 6 is 0. So what remain? X raised to 7. So 1 into x raised to 7, it is what? This one. So this is the new equation you get. Now suppose you want to shift this 1001 towards right by 3 bits, then what it become? Then this decimal point, it would be shifted to over here. So what it becomes? 10. So if you want to represent it in the equation form, then as we know, its equation is x raised to 4 plus x plus 1. And what is remained then? It is x, because this is x raised to 0 into 0, 0, x raised to 1 into x. Sorry, x raised to 1 into 1, it is nothing but your x. So now we would understand the, you know, division using polynomial. Suppose you have a data word x raised to 3 plus 1. Now, as we know that we are going to augment this data word by 3 bits. So it means what? In previous example, you can find it. If we are going to multiply this equation by x raised to 3, you would get this equation. So similarly, we are going to multiply with this data word by using x cube. So what would we got it? X raised to 6 plus x cube. So this is your code word. And over here, this divisor is x cube plus x plus 1. So as we know, we need to cancel this one. So by which, it should be multiply this divisor. So you need to multiply this divisor by x raised to 3. So you get x raised to 6 plus x raised to 4 plus x raised to 3. So this get cancelled. What remained is x raised to 4. Similarly, XORing of two similar bits, it is a 0. So x raised to 4, it is there. So now, by which term you need to multiply this divisor so that you would get x raised to 4 over here. So definitely plus into x. So it would become x raised to 4 plus x square plus x. So this get cancelled as XORing of these two. What remain? It is x square plus x. So this is the remainder, and we are going to append this remainder to this one, and what you would get, it is your code word. So the divisor in a cyclic code is normally called the generator polynomial. Now last topic is the cyclic code analysis. Now to find the capabilities, of the coding by means of this polynomial. So we define the following: f of x is nothing but your polynomial with its binary coefficients. So you should know this. Data word is represented by dx, code word by cx, generator in the encoder it is gx, syndrome in the decoder, and ex, it is the error that is being introduced during transmission. So in a cyclic code, if s of x, that is a syndrome, is not equal to 0, then what does it means, guys? That one or more bits is corrupted. And what if syndrome it is a 0? It means no bit is corrupted. Or else some bits are corrupted, as we have already seen in a previous lecture, but the decoder failed to detect them, because these changes, these corruption in such a way that it creates a new valid code word which is present in that valid list, although its value is different. So decoder can't detect those errors, although the error is being introduced. So as we know, the receive code word, it is represented by this cx plus ex, that is your code word plus error. And the first term, and the received code word, it is a sum of this send code word and the error. And the receiver, it divides this receive code word by means of g of x, that is your generator, to get this syndrome, that is checker. So receive code word is nothing but your cx upon gx, and this is ex upon gx. So the first term at the right hand side of the equality, it has a remainder of a 0. So the syndrome is actually the remainder of the what? Second term on this right hand side. If this term, it doesn't have a remainder, it means syndrome is equal to 0. Either ex is 0 or ex is divisible by gx. So we don't need to worry about this first case. The second case, over it is very, very important. The errors that are divisible by this gx are not caught. It may happen. because I already told in your previous lecture that if you are getting the syndrome value, you know it is a 0, and the code word it is being changed, but it is present in that valid code list, then we couldn't identify that error. So in cyclic code, those errors that are divisible by g of x are not detectable, are not caught. And remember, if the generator has more than one term and the coefficient of x raised to 0 is 1, then all the single errors, it can be detected. This is the standard polynomial table. So in today's lecture, we have seen about the cyclic codes, why we are telling it as a cyclic codes. Then we have seen the encoder and the decoder of your cyclic codes, that is cyclic redundancy check. Then we have seen what is polynomial, the basics of polynomial. Then we have seen the polynomial division, what is cyclic code analysis. So this is an assignment that you need to solve it. So please note down this assignment. In next module, we are going to see about a checksum. This is my email address shared on the screen. And thank you very much, students, for today's lecture.